tangent of 0 is 0. Tangent of 30 degrees is... It sounds like we need a flashcard quiz tomorrow. Give you some motivation to study those. What do you think? Radical 3 over 3, good. Tangent of pi over 4 is 1. Tangent of pi over 3 is just radical 3, and tangent of pi over 2 is undefined. If we keep going through that, first of all, remember, what's the next angle that brings you into the second quadrant? We have 0, pi over 6, pi over 4, pi over 3, pi over 2. What's next? It's got a 60-degree reference. Joey? 13 pi over 6? No, because a couple things wrong with that. 13 pi over 6 has a reference of pi over 6. We're looking for a reference of pi over 3. And 13 pi over 6 would be a full circle and then some. So you're just, you know what you gave me? You gave me the coterminal to pi over 6. But we want the next angle, which is going to be a pi over 3 type. If this was 1 pi over 3, this is 2 pi over 3. And that would be 3 pi over 3. Okay, so 2 pi over 3 is our next. Followed by something that's going to have a pi over 4 reference. And again, 1 pi over 4, 2 pi over 4, 3 pi over 4 is where we're at. And then this would be 4 pi over 4. And then, what would the next critical angle be? Kenzie. 5 pi over 6, because this is 6 pi over 6, so we're one tick before that, 5 pi over 6, good. And then we would just be at pi. So let's go around the room now. What would that be, Marissa? Wrong reference angle. Pi over 3s are your 60s. So when we're going around, it's like a 30, 45, 60, 90, and then it starts backtracking 60, 45, 30, 0. Then it starts counting back up. Very good. 7 pi over 6. Morgan, what would be next? Very good. 5 pi over 4. Mitch, what would be next? Very good. And then that brings us to 3 pi over 2. And we're leaving that third quadrant, and then the first one in the fourth quadrant. Olivia? Yep, 5 pi over 3, very good. Nate, what would be next? What's the reference of it? Is it a pi over 6, pi over 4, or a pi over 3 angle? Pi over 4. So how many pi's over 4 is this one? No. 4 pi over 4. Pi is just going to be 4 pi over 4. That's half of the circle. So a full circle would be how many pi's over 4? A half circle is 1 pi. A full circle is 2 pi. So how many pi's over 4 would be 2 pi? No. something pi divided by 4 has to be the whole number 2. What number divided by 4 gives you 2? 8. So that would be an 8 pi over 4. And we're one tick prior to that. So 7 pi over 4. Good. And the last one, Trista. Good. And then you get your full 2 pi. So right, when you're talking about pi's over 6, this is 6 pi over 6. And this one's 12 pi over 6. 6 pi over 6, 12 pi over 6, then one tick before that would be 11 pi over 6. Okay, so now all of our numbers are going to match the numbers of the reference angle, give or take a minus sign. And based on all students take calculus, all of our second quadrant angles are going to be negatives. And all of our fourth quadrant angles are going to be negatives. And all of our third quadrants will be positive. So the 2 pi over 3 is going to just be the pi over 3 value, radical 3, but just with a negative. 3 pi over 4 is just going to be negative 1. 5 pi over 6 is just going to be negative root 3 over 3. And pi has a reference angle of 0, so it's just going to follow the tan of 0, which is 0. Didn't really need the negative sign on that. So this is Q1, this is Q2, we jump into Q3, so we're positive again, so 7 pi over 6 is going to be the same as pi over 6, pi over 4, pi over 3, and then undefined again. And then 5 pi over 3 is going to mimic the pi over 3, but with a negative, a 1, a root 3 over 3, and a 0. So graphing this, first and foremost, the undefines are asymptotes. So we have an asymptote at pi over 2. And 3 pi over 2. And then we have the point 0, 0. Root 3 over 3, we kind of need to know approximately, because remember our y-axis is counting by actual numbers, whereas our x-axis is counting on that pi scale. So root 3 over 3 on my calculator is about 577. So I'm going to call this, I'll count by ones. 1, 2, 3, 4, and 5. So pi over 6, which is about a third of the way to pi over 2, right? 30 degrees as compares to 90 degrees. And then 0.577, so that's right around there-ish. Pi over 4 is at 1. Pi over 3 is at root 3, which is 1.7. And that's kind of all we see so far there. When you get past pi over 2, 2 pi over 3, which again is like a third of the way to pi, is negative root 3, so that's negative 1.7. 3 pi over 4 goes with negative 1. 5 pi over 6 goes to negative root 3 over 3, which is negative 0.5-ish. Pi is 0. 7 pi over 6 is root 3 over 3, so the 0.577 again. 5 pi over 4 goes with 1. 4 pi over 3 goes with root 3, which is 1.7-ish. So this is actually more helpful than that first section, because that first section was only half of a cycle. This is really where you'll remember kind of that tangent shape. And then to finish it off on this side, 5 pi over 3 negative root 3. Negative 1. Negative root 3 over 3. And then 2 pi is 0 again. So that does that. And this does that. So that's really your first, that's just your first rotation around the circle in the positive direction. That's quadrants 1 through 4. If you kind of go backwards, then this is just all going to repeat itself, right? Because this graph's about to repeat itself. So if I take this and just kind of translate it over, this is going to complete this, and we're going to have an asymptote at negative pi over 2 and negative 3 pi over 2. And then that pattern continues. You definitely didn't do as much with tangent last year. It looks different enough where this should look familiar. So, what is the amplitude? Sarah, what would you say the amplitude is of a tangent graph? Amplitude has to be a number. It's kind of a trick question, though. Right. It doesn't really have an amplitude. We don't talk about amplitude with tangents. It does have a period. What's the period, would you say, Connor? Meaning the length of space it takes for this cycle to repeat. Just pi, right. And that really is tied in with the fact that your quadrants are kind of opposite each other. So you have a positive quadrant, a negative quadrant, a positive quadrant, a negative quadrant. So it's already repeating once you get to the pi. Positive to negative, and then it keeps going positive to negative, and then positive. So it's already repeating, versus with like a sine and a cosine, it's positive, positive, negative, negative, and then the repetition starts for sine. And for cosine, it's positive, negative, negative, positive, and then the repetition starts. Positive, negative, negative, positive. So it's really kind of has to do with that. So your period is just pi. So here's the thing. The period formula for sine and cosine is 2 pi over b. Because your period for those is 2 pi, and then depending on what b is, the horizontal stretch or compression, that changes your period. Versus for tangent graphs, the calculation is period equals pi over b. Because it's originally pi, and that gets stretched or compressed accordingly. The phase shift, obviously the parent graph doesn't have a phase shift, and the parent graph, I'm not really sure it's called a midline. We're going to go with it, because it's still the middle of the graph. If you can, well, it's not really. See, that's the technicality. If it's going to negative infinity and to positive infinity, there really is truly no middle of it, but that's kind of where the inflection changes. Like it's almost looking like a parabola that opens down, and then it kind of swivels and looks like a parabola opening up. Almost like a triple root kind of squiggle. So that midline, obviously, or that kind of central point is right at the x-axis and can get shifted up or down. Okay? Cotangent is the reciprocal function. Now, this is the first reciprocal function we're doing. We haven't done cosecant and secant yet. That's tomorrow. But with tangent, we're going to do the cotangent on the same day, which is essentially just reciprocating all of your y values. So 0, 0, what happens when you reciprocate 0? What's 0, the reciprocal of 0? Andrew? Undefined. The reciprocal of 0 is undefined. So what actually happens is all of these zeros actually become your new asymptotes when you're dealing with a cotangent graph. So any place you see a 0 up here becomes an asymptote on the cotangent graph. So that's going to be at 0, at pi, at 2 pi, at negative pi and negative 2 pi. So that really reciprocates all of the zeros. The other thought is, what reciprocates an undefined? What's the reciprocal of undefined? Think of undefined as like a number divided by 0. If you flip that, that's going to be 0 divided by the number, which is always going to be 0. So any place where you see these asymptotes are going to be the new zeros of your cotangent. So at pi over 2, you're going to have a 0, 3 pi over 2, negative pi over 2, and negative 3 pi over 2. Perfectly halfway in between the asymptotes again. So that covers those. And then the reciprocal of root 3 over 3 is 3 over root 3, 1.7. So pi over 6 is going to go to a 1.7-ish. For pi over 4 and 1, the reciprocal of 1 is still 1. For pi over 3 and root 3, which was on the tangent graph, the reciprocal of root 3 is 1 divided by root 3, which is 0.577, so 0.6. And then we hit the 0. And then the reciprocal of 2 pi over 3, this negative root 3, is going to be negative 0.6. The reciprocal of negative 1 is still negative 1. And the reciprocal of negative root 3 over 3 is negative 1.7. So, how can you describe, other than the location of the zeros and the asymptotes, how can you describe the difference between tangent graphs and cotangent graphs? Tangent graphs are always blank, and cotangent graphs are always doing the opposite. What am I looking for, Bridget? What do you think? Increasing. Always increasing. Parent graph anyway. Always decreasing. Obviously, if you do a negative tangent graph and it flipped it upside down, it would be decreasing. Or even if you horizontally flipped it, it would be decreasing. But as far as the parent graph is concerned, tangent graphs always increase. Cotangent graphs always decrease. And then this pattern obviously just continues. Throughout, on top of them kind of being shifted one way or the other because the asymptotes and zeros are flip-flopped. Good? Okay. So those are your parent graphs. We flip to the back and actually have to sketch a graph of the tangent, 2 tangent of x over 2. So We can't really talk about amplitude. We do talk about period. The period is not 2 pi over b anymore, it's pi over b. And b in this case is what, John? Nope. This is 2 tangent of what x? What number is technically there? If I were to rewrite this as the tangent of blank x, what would be the same? You keep looking, sounding like you're trying to say 2, right? But if I put a 2x, is 2x the same as x over 2? No. Dividing by 2 is the same as multiplying by what? 1/2. There's your coefficient, 1/2. There's your b value. So pi over 1/2 is just 2 pi. So after this horizontal stretch, your period isn't pi anymore, it's 2 pi. Okay? So if you think about tangent a little bit differently, it's hard to think of your cycle starting at 0 and ending at pi because it kind of splits it up. So if you think of in a parent graph, it starts at negative pi over 2 and it ends at positive pi over 2. This one is stretched horizontally by a factor of 2. So it's actually going to start at where? Where would you say? If we horizontally were to stretch this by a factor of 2, where is this vertical asymptote going to move? If you stretch it out by 2. Andrew? Negative pi, and this one is going to go to positive pi. So we have an asymptote at negative pi and positive pi. They're dictating my domain here, and it's definitely heavier on the positive side. So I'm going to put my y-axis more towards the left just to accommodate that. I'll go negative pi, positive pi, 2 pi, 3 pi. So my cycle will start at negative pi, and it's going to end 2 pi units later, which is at positive pi. So asymptotes at negative pi, and then every 2 pi after that. So at positive pi and at 3 pi. Now, as far as this vertical stretch is concerned, it's a little bit different than amplitude. I can't just like let this wave go up to 2 and down to negative 2 because these go to infinity anyway. I do know that my zeros are halfway between my asymptotes. And then normally it hits 1, right? It's like your pi over 4, 1. But in this case, because it's stretched by 2, that 1 is just going to double up to 2, and this negative 1 is going to double down to negative 2, and it's just going to be a little bit taller and skinnier than it would be otherwise, but it's pretty subtle. So your critical points, I would say, are obviously your zeros and your asymptotes, but also that one additional point, which is going to kind of jive with what would normally be on your parent graph, the pi over 4, 1. You're not going to need to you don't need to do too much with these guys because they're decimals and you don't have a calculator. But anything that's going to be a pi over 4 type tangent, which should be 1, when it gets vertically stretched is now 2. But notice that's not happening at pi over 4 here. Where is it happening? What x coordinate is this? 0 and pi. So what's this, Bailey? What's halfway between 0 and pi? Pi over 2, right? On the parent graph, it's pi over 4 comma 1. Here it's pi over 2 because we've, again, doubled everything out. We've had a horizontal stretch out. But at any rate, it's always going to be halfway between your 0 and your asymptote. You know, that's all you need to really know. Whatever unit is halfway in between those is going to be your 1 or your 2 in this case because of the vertical stretch. And then just repeat that. And they only wanted this from negative pi to 3 pi. Okay? So I do these a little bit differently because my cycle doesn't really involve the phase shift much. I kind of think of my parent graph starts at negative pi over 2 and ends at pi over 2. And then how is that going to shift out? Stretch out or in horizontally. Okay, and then the last one, cotangent. So we have a vertical stretch, which we'll deal with, and we have a horizontal compression. So our vertical asymptotes here are usually at 0, pi, 2 pi, etc. But if we're horizontally compressing, our new vertical asymptotes are going to be where? Aiden. Yep. So the 0 one, when you horizontally compress it by 2, is still 0. The pi over 2. Pi, and so on. So they want 2 full periods, so I'm going to start right at 0. And I'm going to 0, pi over 2. Every time I reach a new asymptote, that's a new period. So I'm good with that. So I did do this one a little bit differently, and it's really whatever you're comfortable with. In the previous one, I did period equals pi over b, which would be pi over 2 in this case. So knowing that your asymptote is at 0, every pi over 2 units would put your asymptotes at pi over 2 and pi accordingly. And then your zeros, again, are halfway in between those. And then rather than increasing the whole time, this is decreasing the whole time. Rather than being at, pi over 4 comma 1, there's a stretch by 3. So what is here, I'm going to bring up to 3. And here I'm going to bring down to negative 3. And again, I'm not going to worry about any other points. So the more it's vertically stretched, the less you're going to see a swervy kind of thing. It looks flatter and flatter the more you stretch it, which should make sense. Any questions? You're good? All right, so your homework's there at the bottom.